Okay, so that was a perspective on the nature of mathematics. What is the nature of knowledge and learning? What allows us to behave in accordance with a rule or principle such that we can solve mathematical problems correctly? Well, the classical answer to this is that we use the rules as such, following them by appealing to them as we think. If the rule or principle is not given a priori, then there must be a eureka moment when it is discovered or induced. So, for example, Izard et al., in a paper on knowledge of the cardinality principle, wrote that the exact nature of the insight that children experience when they reach the state of being cardinal principle knowers is unclear. In order to understand it better, we need to determine what children know just before this insight, what triggers it, and what they finally derive from their newly acquired numeric competencies. I see this statement as capturing this implicit commitment to the notion that we use these rules as such and acquire them as rules. Now, there is an alternative vision, and this was the vision Rumelhart and I explored in our paper on learning the past tense of English in the PDP books. According to this alternative, we gradually acquire implicit encoding and responding abilities that can be described by rules, guided by an environment that encourages these tendencies. And we argue that deep neural networks or PDP models can capture these kinds of characteristics. Here I'm showing an example of such a deep neural network. By deep, I mean a neural network that has at least 2 layers of modifiable weights. Some would say, oh, that's still shallow, you need more than 2, but 2 is a minimum to capture, I think, the essential characteristics of the capabilities of neural nets, and indeed deeper may be better in many circumstances. But this little model, which essentially explores an application of the same ideas that Rumelhart and I explored in 1986, captures these ideas in the context of a model that learns to map from spellings of words to their sounds. This model is trained using examples of the spellings of words and their pronunciations using a simple gradient descent learning rule. And through the course of the gradual evolution of these connection weights, it develops the ability to read familiar words correctly and also to read items that it's never seen before in a way that's consistent with the spelling sound correspondences that are exhibited by other words. So the item vint, which wouldn't have been in the training set, would be read correctly by this network, exhibiting knowledge that could be described by rules, but is not encoded in rules as such. Now, there are some key characteristics of multi-layer neural networks, as we've explored in a paper with Andrew Sachs and Surya Ganguly. These models exhibit a nonlinear dependency between the strength of existing knowledge and how rapidly they can learn. And I'm going to argue that this can help us understand why learning can be slow at first, how stage transitions can occur, and why we see interesting changes in readiness to learn in children at different ages, and even though they may still seem to be, in some sense, within the same stage of their thought. So the essential idea is this. When we train a network like this, we present an input pattern, we propagate it forward from the input, shown at the lower level of the diagram, through the hidden layer by way of the first set of connection weights, the matrix W21, and then from there to the output by way of the second matrix, W32. This produces an output O, and The environment may provide us with a teaching signal, in this case, perhaps the correct pronunciation of the item represented on the input. And that gives us an error, which is the difference between the teaching signal and our output. Now we learn by adjusting the connection weights to reduce this error. And the key point is that the extent of the adjustments that we make depends on the knowledge that's already in the connections. So the change we make to the input weights, that's the first equation below the diagram there, the weights from the input to the hidden layer, depends on the existing values of the weights from the hidden layers to the output. And likewise, the changes that we make to the weights from the hidden layer to the output depend on the existing values of the weights from the input to the hidden layer. If one of those sets of weights was identically zero, there would be no signal being propagated through the network. If they start with very small random values, learning is slow at first. And once they begin to get structured through experience, they propagate information that then can be used to allow the other layers of weights to change. I'm going to illustrate these ideas by describing a case study of work I did some years ago, building off of work by Bob Siegler at Carnegie Mellon University. Bob looked at children's performance in a task originally introduced by Piaget and Inhelder, and in this task, the child sees a physical scale with a bar sitting on a fulcrum, and there are 5 pegs on each side of the fulcrum, spaced evenly, and then some number of weights is placed on one of the pegs to the left of the fulcrum, and some other number of weights may be placed on one of the pegs to the right of the fulcrum. The whole thing is immobilized so that it can't actually move, but the child is asked to say which side of the scale would go down if it was free to move. And Siegler tested children at several different age ranges from 3 to adulthood, and observed that there is a stage of development that lasts for a couple years in which children essentially respond based only on the number of weights on each side of the scale. And that could be characterized by a simple rule he called Rule 1. Weight, in this case, is the dominant dimension. So if the dominant dimension is equal on both sides of the scale, then you'd say balance. Otherwise, you'd say the side with the greater value will be the side that goes down. Now, when children are a little older, they begin to exhibit sensitivity to distance. And this is indicated by the fact that when the weights are the same, they will take distance into account. So that could be characterized also by a rule, which Siegler called Rule 2. I asked the question, are children really using rules, or is there perhaps a more connectionist-like substrate underlying this performance? And there were several hints in the data that led me to think that perhaps this was a useful approach. First, children's performance often scores in accordance with simple rules, but there are often subtle discrepancies. Secondly, children are sensitive to the amount of difference in distance, and the degree to which they are sensitive to this does increase with age. So it appears that there may be some graded change in their sensitivity to the distance cue. Children's explanations are often consistent with their choices, and that was taken as evidence that they actually behave in accordance with this rule, but they aren't always consistent with their choices. And in other situations, they're often quite inconsistent with children's choices. And so that raises the question of whether or not the rules, the stated explanations, are post hoc explanations that aren't necessarily the basis on which responding actually occurs. Another very interesting finding is that within children who are scored according to Siegler's procedures as, using Rule 1, older children progress from training with conflict problems, while younger children do not. So I developed a little neural network version of a balanced scale model. The network has input units. It has a set of input units, one for each of the possible numbers of weights on the left, and another one for each of the possible numbers of weights on the right. So for example, in the problem shown here, where there's 3 weights on the left, the unit for 3 weights on the left is activated, and where there's 4 weights on the right, the unit for 4 on the right is activated. It also has input units for the distance of the weights from the fulcrum on the left, and for the distance of the weights from the fulcrum on the right. The model's task is to activate the output unit for the side that should go down, given the weights and distances represented in its input. And if they should balance, it should set the activation of both of the output units equal to 0.5. The network's initialized with small random values in the connection weights from the input units to the hidden units that you see, and then in the connections from those hidden units to the output units. And it's trained with the full set of possible problems in this space, but with a bias that favors learning about weight before distance. And that bias is that problems in which weight differs between the two sides occur more often than problems in which the distance differ. So using this model, I found that learning is actually essentially continuous. Each pattern presentation produces small changes in the connection weights. And as learning progresses, there is a graded change in the connections that demonstrates an increasing and graded sensitivity to the different cues. The change in the weight cues is earlier and more rapid than the change in the distance cue, as you can see here in the diagrams on the right, which are essentially telling you the magnitude of the difference in the connection weights that's associated with a difference in the number of weights or a difference in the distances. And I've shown this separately for the connection weights from the input layer to the hidden layer below and from the hidden layer to the output layer above. In these results, the performance of the network, scored against the same criteria that Siegler used to score children, matches Rule 1 from about epoch 20 to about epoch 40, where an epoch is one sweep through the full set of training examples. I then conducted a version of Siegler's experiment about differential readiness to learn. So I took the network in its state of knowledge at epoch 20, where it had just entered Rule 1, and I presented it with a set of conflict problems. So these are all problems in which if you only paid attention to weight, you'd choose one side to go down. If you only paid attention to distance, you'd choose the other side to go down. But in fact, among the set of 15 problems, in 5 cases, the side with greater weight will be the side that should go down. And in another 5 cases, the side with the greater distance would be the side that should go down. And in the remaining 5 cases, the scale should actually balance. For example, 4 weights on peg 2 versus 2 weights on peg 4. So with these problems, if you were relying just on the weight cue to make your judgment, you would say the side with the greater weight should go down every time, and you'd only be right 1/3 of the time. Under those circumstances, the network at epoch 20 actually shows regression in its behavior towards guessing. It gets worse in its ability to use the weight cue and doesn't really show progress in its ability to use the distance cue. But if I train the network with the same set of conflict problems at epoch 40, it actually progresses onward to Rule 2. Yes, initially it's making the incorrect prediction, But the error signal, because the connection strengths on the distance side of the network have begun to build up, can actually strengthen its tendency to rely on the distance cue to reduce its error, while any negative feedback on the weight cue, while maybe a little bit deleterious, is not enough to overcome the strong strength of that cue. And so what happens is the network essentially preserves its ability to rely on weight when only weight is varying, but also can now rely on distance when distance is varying and weight is held constant. So the very same network with the very same intervention will progress differently depending on its prior experience that's built into its connection weights. And this experience builds up gradually over developmental time. It doesn't necessarily show up in overt measures of what stage of development or rules we might be using. So, as an interim summary, I'd like to suggest that the ability to act in accordance with principles or rules can emerge through a subsymbolic learning process in a neural network. And these models exhibit properties that can help explain gradual, sometimes punctuated looking development, graded sensitivity to quantitative variables, and changes in readiness to learn with experience. Now I'd like to describe some findings from research on mathematical cognition, interpreted and modeled from a PDP perspective. The first question I'd like to discuss research related to is the question of, are approximate and exact number concepts innate? Many people hold that humans and animals are endowed with an innate approximate number sense. And there is a signature characteristic of this sense, which is sensitivity to the ratio of the number of things rather than their exact difference, that characterizes the behavioral performance of adult humans, many species of animals, and young children. So, for example, in the displays you see here, if asked to say which of the sets of dots is larger, you might have a tendency to say the left one, and you'd probably be right. And that tendency doesn't depend on the exact difference in the number of dots on the two sides, but the ratio of the numbers of dots. So we can tell 10 from 7 about equally well as 100 from 70, for example. However, there are some indications that the approximate number sense is experience dependent. One such indication is that acuity of this sense is both age and culture or schooling dependent. So here I'm illustrating results from a recent experiment by Odick et al., in which they measured sensitivity to differences in numerosity at many different ages, from about 3 to 20, and they also included a data point based on previous research with infants, showing that the Weber fraction, or essentially the ratio that was discriminable, becomes more and more refined with age. So young children exhibit a Weber fraction of about 1, or the ratio they can discriminate is about a 2 to 1 ratio, whereas adults exhibit a Weber fraction of about 0.14, about equivalent to a ratio of 7 to 8. Furthermore, recent publication by Pica et al., looking at uneducated Munduruku adults from the Amazon basin in Colombia, found that on average their Weber fraction was about 0.33, or approximately the same as what you see in 4 or 5-year-olds. So it now appears, in fact, that this sense is strongly influenced by experience. In fact, it's possible to show that a very generic neural network will exhibit tendencies very similar to that seen by children, even if it's not actually trained to represent numerosity per se. So this was first demonstrated in an important paper by Stoyanov and Zorzi in 2012. They used the neural network shown here and presented it with displays like those that you see. The displays contained variable numbers of objects with variable area. And the task of the network was simply to form an internal representation that could be used to reconstruct the actual input. So there was no explicit instruction to worry about how many blobs there were or explicitly to encode the size of the blobs. But the neural network essentially learned connection weights from a visible layer to a first hidden layer, and then from the first hidden layer to a second hidden layer that allowed that representation at the second hidden layer to be played back to reproduce a close approximation of the actual input that was presented to the network. They then simply asked, can we use the patterns of activation on the second hidden layer of the network to answer the question whether the number of objects in the input is greater than or less than some criterial number, let's say 8. And indeed, they found that the network could support a adult-like performance with a Weber fraction of 0.14, and this ratio signature after the network had been trained without any reference whatsoever to representing number. In some extensions that we've done of these simulations, we find that networks like this can perform as well as 3-year-olds even before any training occurs whatsoever. So if we initialize the connection weights in the 2-layer network at random, we can find a value that will result in a network that can sustain a Weber fraction of about 0.5, which is approximately what's seen by 3-year-old children, only based on the random initial weights. From there, the network can gradually refine its acuity through an incremental unsupervised learning process. And that's illustrated on this graph. So in blue and green, we've shown results from earlier studies, including the data point estimated from infant studies from Odick et al. And data points from their study and another study by Piazza et al. And in red, we've shown our simulation, which, as I said before, with random initial weights, performs at about the level of a 3-year-old, and with progressive learning becomes better and better, and actually exceeds adult performance at this task at the end of training. So this work suggests that perhaps a generic neural network mechanism, rather than a number-specific mechanism, can support this important cognitive ability. Now, it has to be understood that a classifier is being trained to use the patterns on the hidden layer to classify the responses. And some debate could arise about how much we've snuck in under the rug through that. So the jury may still be out on whether there's any reason at all to believe in an innate approximate number system. But these results lead me to think that it's possible that the representations we draw on that support this ability that we see in primitive form in infants and we see in many species of animals does not depend on something innately given for the purpose of processing number. What about exact number? You know, the idea that you can have exactly 1 or exactly 5 or exactly 7,423 objects. Well, some once thought that an understanding of counting and exact natural numbers was innate. But individuals from cultures lacking counting systems fail basic tests of counting principles, as was established by an important study by Peter Gordon in 2004. So many now suppose that an understanding of exact numbers also culturally transmitted. And indeed, our culture invests a huge amount in instructional materials designed to help children learn to count. Within this context, though, we can ask, does learning to count involve an inductive leap, the discovery of a rule or principle? And indeed, this idea that it involves a semantic induction has been the subject of intense investigation by others. Sarnecka and Carey, 2008, argued that children make a semantic induction of the cardinality principle at around the age of 4, and they supported this claim by showing that kids who could succeed at what they considered a criterial task for this ability also tended to succeed at other tasks indicative of understanding of the cardinality principle. So the index task, the give-n task, is simply a task where you say to the child, oh, here's a stack of, let's say, little plastic lemons. Can you give me 6 lemons? If the child can reliably give you n for numbers in the range of 6, 7, or 8, they're said to be able to succeed at the give-n task for arbitrary n, of course, as long as it's within their count range. So children may not be able to count that much above 10, but if they can succeed at the give-n task within their count range, then they're said, according to Sarnecka and Carey, to understand the cardinality principle. And indeed, systems possessing symbolic computational primitives that use probabilistic inference to figure out what's the best computational procedure among several alternatives to account for observed data can show this kind of inductive leap, as Piantadosi et al. Showed in a nice paper in 2012. But it's not actually clear whether counting really involves such an induction. There was an important paper by Davidson, Eng, and Barner in which they argued that, in fact, the understanding of exact number emerges very gradually. They looked at children who can correctly give n for numbers in the range of 6 to 8, and all of these children could count at least to 10. And they then tested children on what's called the unit test of CP knowledge, cardinal principle knowledge, from Sarnecka and Carey. And this test goes like this. The child is shown a set of 5 objects, let's say, being placed into a little box. Then the experimenter demonstrates the addition of one more object into the box and says, okay, now, do I have 6 or do I have 7? So the child knows the count list and he knows that 6 comes after 5. If he knew the cardinality principle, he should be able to pass this test. But in fact, many of the children who succeed at the give-n task for numbers in the 6 to 8 range and who can count to 10 still perform a chance in this unit task. Children with larger count lists could succeed in the unit task with smaller numbers, and as their count list grew, the numbers they could succeed with grew, but there was generally their ability to do the unit task didn't extend all the way up to the end of the range of their count lists. So it didn't look as though they actually had a general understanding of the successor principle as indicated by this task. There were several other tasks that showed similar results, and so the authors proposed that children only achieve a general understanding of exact number after considerable experience. And we can ask, should we see this as resulting from an induction of a principle of cardinality or from the gradual emergence of a cognitive ability that might be understood as gradual weight change within a neural network? Let me extend these points with some observations in geometry. First of all, it's been noted by some Dutch researchers, whose name I pronounce badly is Van Healy, and replicated by some American researchers, including Berger and Shaughnessy, that geometric understanding develops very gradually with age. And Van Healy characterized this development in terms of a series of levels. One of the things that was found in the research in the US was that a year's course in geometry had no special impact on a student's level. In fact, many good high school geometry students had not been able to reach what Van Healy called level 4, which was associated with an understanding of what it means to prove something and to being able to reason systematically using mathematical argumentation. In fact, Berger and Shaughnessy concluded that there was often a complete mismatch between what teachers thought they were trying to convey to students in terms of principles of proof and systematic reasoning, and what students were able to learn when they took their geometry classes. Similar kinds of observations come from a paper by Golden et al., which they entitled Failure of a Didactic Exercise. In their paper, they walked students through the Socratic dialogue that's recorded in Plato on how to create a square with twice the area of a given square. So in this dialogue, Socrates is attempting to convince his friend Meno that we have an innate understanding of the principles of geometry. And in order to convince his friend of this, he purportedly elicits an understanding of how to create a square with twice the area of a given square from Meno's slave. Now, as the dialogue unfolds, Meno's slave actually exhibits a large number of incorrect ideas, which Socrates then rebuts with arguments that the slave can understand and accept, and gradually walks the slave through to the point where the slave attests to an understanding of the correct procedure for constructing a square with twice the area of a given square. In brief, this is how it works. Here's our given square. Observe that if we put a diagonal through this square, we will create two triangles, each with an area equal to half that of the given square. If we then create three more squares like the original squares, and then draw diagonals through each of them, we'll end up with a square in the middle, of course tilted by 45 degrees, which has clearly twice the area of each of the contributing squares. Meno's slave agreed to this and said he understood it. And so did the students in Golden et al.'s experiment. Yet they found that in spite of professing this understanding after the experiment, the students who exhibited many prior misconceptions similar to those of Meno's slaves could not demonstrate the solution on a new square right after they'd been shown this thing that they purported to understand. So they said, this actually didn't create learning. And we see a similar pattern after a brief lesson in trigonometry. But there is a positive side to this. Those who exhibited fewer misconceptions in Golden et al. Studies were actually fairly good after the lesson at constructing a square with twice the area of a new given square. And similarly, in our study of trigonometry, those students who did somewhat better than chance in a pretest showed a good ability to benefit from a brief lesson. Whereas those, even though all the students had actually been exposed to quite a lot of trigonometric instruction before, those students who performed near chance on the pretest were not able to benefit from the brief lesson. So to me, these results all go together with the general idea that our ability to progress from a didactic experience depends on our state of mind, that these abilities are things that build up slowly and yet can be pushed along, showing insight-like transitions if we're in a state of appropriate readiness for that. So, as an interim conclusion, I'd like to suggest that the PDP perspective seems consistent with findings across many domains of mathematics. And based on that, it might be worthwhile to see if we can develop the approach further.